Everyone can solve the first integral, but can you solve the second one? So in this video, we have this integral x sine x by 1 plus cos square x dx. In the first one, we have integral from 0 to pi. In the second one, we have integral from 0 to pi by 2. And the limits of integration is what makes the difference, because this pi is carefully chosen so that we can make clever use of the King's rule, and this simplifies a lot. But the second one tends to be a bit longer. Yeah. And the solution for second integral goes to sussy-susan, who gave me the solution in the community section of my channel. And yeah, now let's begin. So first one, for the first one, what you should do is just notice what happens if we use the King's rule. Yeah. So if you use the King's rule, we can basically eliminate this x that is in front of x sine x, and then that is all what makes it easier. I guess you probably know that the King's rule is stated in this way: integral from a to b of f of x dx. This is equal to integral from a to b of f of a plus b minus x dx. And you can easily prove this by taking the antiderivative. You will see that both give the same answer. Now if you know this, our integral, the first integral, will also be equal to integral from 0 to pi of pi minus x. Yes. And now sine of pi minus x is just sine x again. And also cos of pi minus x is minus cos x. But since there is an square, that will again just be 1 plus cos square x. Yes. Dx. Now if we add these two integrals, we get the following result. Over here we see that sine x by 1 plus cos square x is the same, so x plus pi minus x is just pi. So this is integral from 0 to pi of pi times sine x by 1 plus cos square x dx. Yes. Now after this, you just need some easy u substitutions and you get the answer. So if now you substitute u as cos x, then you are definitely going to get solution. This will be integral from 1 to minus 1, and then pi, now sin x dx will just be minus du by 1 plus u square. Yes. Now the negative sign can be used to reflect the limits of integral, and we get 2i is equals to pi times integral from minus 1 to 1 du by 1 plus u square. Now I guess you know how to solve this integral. 2i is equals to pi times, this will be tan inverse u. Yes. And tan inverse u going from minus 1 to 1, so this is 2i is equals to pi times tan inverse of 1 is pi by 4 minus pi by 4, so let me write that plus pi by 4. So we get the answer. Now this is pi by 2, and pi times pi by 2 is pi square by 2, and also if this 2 goes to other side, we get pi square by 4. That is the answer. So you see that if you just use King's rule, the first integral becomes too easy to solve. Just a u substitution and it gives the answer. But let's see how we can solve the second integral. Be aware that it's gonna be long, but yeah, keep up with me, we will definitely solve it. Now the next solution, next integral, we have I is equals to integral from 0 to pi by 2 x sine x by 1 plus cos square x. Yes. Dx. And now what I will try to do is, I will try to use the integration by parts so as to simplify this x. We get I is equals to x times, now the integral of this thing is, if we take cos x as u, we know that this is going to be minus du, so that's why that will just be minus tan inverse of u, which is cos x. Yes. And now this goes from 0 to pi by 2 minus, over here we have integral from 0 to pi by 2, the derivative of x is just 1, and this other thing is again minus tan inverse cos x dx. Yes. Okay. Now I is At pi by 2, this cos of pi by 2 is 0, so n tan inverse of pi by 2 is also 0, so pi by 2 times 0 will just be 0. And at 0, this one will be 0, but this one will be cos of 0 is 1, and tan inverse 1 is pi by 4. Yes, and again 0 times pi by 4 will just be 0, so 0 plus 0. Yeah, and then over here minus minus will be plus, an integral from 0 to pi by 2. Tan inverse, I can write it as arctan, they are the same, arctan of cos x dx. Okay, good. Now I finally see that I need to solve this integral. I is equals to arctan of cos x dx. Let me introduce a new variable so as to use Feynman's technique while solving. Integral from 0 to pi by 2. Now again, if we again differentiate, we will get to the initial integral, but there won't be a x over there. We don't have this x, and that kind of makes our life easy. So let's do that. Arctan of cos x dx. Okay, now I'm introducing a variable in front of cos x. Okay, so and we want, and note that we just want to find the I of 1. If we find the value of I of 1, that is our required answer. Yeah, if we find the value of I of 1, that is just 0 to pi by 2 arctan of cos x dx, which is what we need over here. Yes. Yeah, so please keep this in mind. Now let's try to solve this. Now if we differentiate this under the integral sign, basically even if I do a complete differentiation over here, when this differentiation goes inside the integral, it will change to partial differentiation, and so that's why we will have 1 by 1 plus a square cos square x. Yes, and then the derivative of a cos x with respect to a is just cos x. Now we can integrate this, yeah, just using the u substitution again. Yeah, we get di by dA will be equal to integral from 0 to pi by 2 cos x by, this will just be 1 plus a square, and then cos square x is again 1 minus sin square x. Yes, so that's why I can say it as 1 plus a square minus a square sin square x dx. Okay, good, looks good. Yes, now what I'm gonna do is I will make a u substitution by substituting u as sin x. Yes, let me substitute u as sin x, and so we get di by dA, or let me just write I dash of a. Yeah, that is simpler. Now I dash of a will just be integral from 0 to, now this is from 0 to 1, and cos x dx is just du by 1 plus a square minus a square u square. Yes, again now this is an easy integral, just in the form of integral of 1 by b square minus x square dx. We know that in this form this integral will just be equals to 1 by 2b ln of b plus x by b minus x. We know this, yeah? So let us use this. So we get I dash of a is equals to 1 by 2, our a is just square root of this thing, so square root of 1 plus a square, and then ln of square root of 1 plus a square plus au by square root of 1 plus a square minus au. Yes, and this is integral from 0 to 1. And also don't forget that since we have a constant in front of the variable, I also need to introduce 1 by that constant number, 1 by a. Just need to do this. Now let me evaluate this from 0 to 1, and then we get I dash of a is equals to 1 by 2a square root of 1 plus a square. Yes, and then ln of square root of 1 plus a square plus a by square root of 1 plus a square minus a, and at 0 these two just go to 0, and dividing this we just get ln of 1. Ln of 1 is 0, we know that. Now I will just try to make a slight simplification over here. If I multiply by square root of 1 plus a square plus a to both numerator and denominator. The denominator will rationalize, and so we get I dash of a as 1 by 2a square root of 1 plus a square, and then ln of this will be square root of 1 plus a square plus a whole square. Yes, now this 2 comes in the front and cancels with the 2 over here. That gives me I dash of a is equals to ln of a plus square root 1 plus a square divided by a square root of 1 plus a square. Okay, good. Now we should not be deviated from our main goal, that our goal was to find I of 1. Yes, so what I can basically do is, if I know that I of 0 is actually 0, yes, over here if I place a as 0, octane of 0 is just 0, so integral will all be 0. So if we know that I of 0 is 0, now what we can now try to find is, if I find this integral from 0 to 1 of I dash of a dA, if I try to find this integral, this will just be I of 1 minus I of 0. Yeah, and since I of 0 is known to be 0, now we can say that this will just be equal to I of 1 minus 0, which is I of 1. Yes, so in our goal of finding I of 1, now what I can try to find is integral from 0 to 1 of I dash of a dA. Yes, so let me try to find that now. And we know that I dash of a is, we know that the I dash of a is just ln of a plus square root of 1 plus a square by a times square root of 1 plus a square dA. Okay, good. This looks good. Now this, to simplify this expression that we have, the probably you might be thinking of substituting a as tan theta, because then 1 plus a square will be just sec square theta. Yes, so let me do that. If we substitute a as tan theta, we get the following expression. This goes from 0. Now tan inverse a will just be pi by 4 over here, and ln of this is tan theta plus, now this is just sec theta by this is again tan theta sec theta. Yes, and dA will be sec square theta d theta. Yes, looks good. Now okay, if we have to go ahead, we know that one of the sec theta cancels out, and now this is just sine by cos, and this is 1 by cos. Cos cancels out, so we just have sine remaining. And even in numerator we can break those to sine and cos. This is sine theta by cos theta, 1 by cos theta, so 1 plus sine theta minus ln of cos theta divided by, this will just be sine theta d theta. Now over here we can actually do something interesting over here, that I hope it will be enjoyable to your eyes to look at what I'm doing now. Ln of 1 plus sine theta by sine theta d theta minus integral from 0 to pi by 4 of ln of cos theta. So okay, this is cos theta by sine theta d theta. Now what I can do something is, we know that this is I of 1. Yes, now if I multiply this expression by 1 minus sine theta, so what, and then something interesting happens, that the terms cancels out and it becomes easier. So let me show you that. Okay, so what I'm gonna do is, if I multiply this by 1 plus 1 minus sine theta and also divide by that, so what I get is ln of 1 minus sine square theta, yeah, by sine theta, and again let me also subtract ln of 1 minus sine theta, ln of 1 minus sine theta by sine theta d theta. Yes, so what I'm actually doing is, I'm just multiplying this by 1 minus sine theta and also dividing by 1 minus sine theta, so that's why this dividing expression comes to negative minus, and then ln of cos theta d theta. Now what's the benefit of doing this? The benefit, you will see it now. The benefit is, now 1 minus sin theta is just cos square theta, and the 2 comes out. Now since there is 2 times ln cos theta by sin theta, and over here there is 1, that expression, these two cancel out, and the cancelling of those expression is not like huge deal, because we just have again 2 expressions again, and one of them with minus sign. But here comes the main idea. So now this will be integral from 0 to pi by 2. Here is 2 ln cos theta, so one of them cancels out, and we just get ln cos theta by sin theta d theta, yes, minus integral from 0 to pi by 4 of ln of 1 minus sin theta by sin theta d theta. Now here comes the deal, that now if we add this expression and this one, now over here this ln cos theta cancels out, and the second one also, like you can take it to the division, and then here will be 1 plus u by 1 minus u kind of expression, and that we have been dealing with since a long time, so that will probably be easier than what we have right now. So let us do that. So 2 times I of 1, now these two cancel out, and we can add these two because they have same denominator, yeah. So integral from 0 to pi by 2, and we get ln of 1 plus sin theta by 1 minus sin theta by sin theta d theta. Okay, good. Now for this, what we can do is, now we can make a new substitution for sin theta first of all, yes. So if we make that, we get x is equals, if we do x is equals to sin theta, then 2 times I of 1 will be integral from 0 to 1 by root 2 ln of 1 plus x by 1 minus x divided by, now sin theta is just x, now theta is sin inverse x, so this will be 1 by root under 1 minus x squared dx. Don't worry, for this getting complicated, this will simplify in just some times. Now after this, again we need to make next substitution, that u is, I guess you know about this substitution, 1 minus x by 1 plus x. The good thing about this substitution is that if we take the inverse, again x will just be 1 minus y by 1 plus y, it will be same thing, and the derivative of this expression will also be, the dx will just be minus 2 by 1 plus u whole square. So this is a well-known substitution. I hope you know about this, yes. If we make that substitution, we get 2 times I of 1 is equals to, now this becomes integral from 1 to, now this is root 2 minus 1 by root 2 plus 1, yes, and root 2 minus 1 by root 2 plus 1, this can again be simplified if we just rationalize this using multiplying by root 2 minus 1. This will be just 2 minus 1, which is 1, so we actually get root 2 minus 1 whole square, yes. So over here we get root 2 minus 1 whole square, and then this is just ln of u, and x is just 1 minus u by 1 plus u, and over here also what we get is 1 plus u square minus 1 minus u square, so 1 by square root of, that will be 2u and 2u, 4u, the other term cancel out, divided by 1 plus u, yes, yeah, and then dx will be minus 2 by, is it 1 plus u, yeah, this is 1 plus u, not square. Now minus 2 by 1 plus u whole square du. Okay, now these two expressions and the square of term over here cancel out, and the remaining terms will be there as it is, yes. Now after this, what I can do is, am I missing something? It seems like I am. Let me see, let me check. Okay, I'm missing something. The thing that I'm missing over here is, here we don't have really 1 minus x or 1 plus x, here we just have the inverse of that, so I should actually get a minus n over here, and these two negative signs cancel out, yes, and the square root of 4 and the 2 cancel out because they are the same, yes. So now we have 2i of 1 as 2 times I of 1 as integral from 1 to root 2 minus 1 square. This is just ln of u by 1 minus u square root of u du. Okay, you can clearly see that now it has become a lot simpler than what it was previously. Yes. And now what you can do is again make a new substitution such that we get rid of this square root sign that's causing a lot of trouble. So let us try to remove that. If I again make a substitution that x is square root of u, then we can make some progress. 2 times I of 1, yes, and the integral, let me write it properly. 2 times I of 1 will just be the integral from 1 to square root of 2 minus 1. Yes. Now in place of ln of u we have ln of x square, so this is 2 times ln of x. Yes. And over here we have 1 minus x square, and square root of u is just x, and du is just 2x dx. Yes. Now it looks a bit simpler. It's getting simpler and simpler now. And now what we can do is again we can take this 4 outside, and that gives us I of 1 is equals to 2 times integral from 1 to root 2 minus 1. Yes. And then this is ln of x by x times 1 minus x square dx. Yes. Okay, so yeah, so we have made quite a good progress till now. Now what I'm going to do is I will now break these integrals into 2 parts. Yeah, one from, okay, so I'm now going to break this into 2 parts. One from 0 to root 2 minus 1, another from 0 to 1. Yes. So I of 1 is equals to 2 times integral from 0 to root 2 minus 1 ln x by, okay, but wait, before that this x also cancels out. I did not notice that, sorry, my bad. So I was wondering like why the expression is different. I was just wondering about that. So this cancels out. Okay, good. Now it looks good. Now ln x by 1 minus x square dx. Yes. And similarly minus integral from 0 to 1 of ln x by 1 minus x square dx. Now the good thing is, if you just notice that second expression is just a standard result, that will make our life easier. So let me show you how this is a well-known result. So the second integral is pretty easy to evaluate, but this first one might scare us a bit, but the second one is easier. So let me show you the second one. Integral from 0 to 1 of ln x by 1 minus x square dx. Let me try to solve this. So what I can try to do is I can try to change this to sum. Yes, directly if you know about the formulas involving polylog, that will be easier. But even if you don't know, you can go it this way: ln x times sum from n equals to 1 to infinity, this will n equals to 0 to infinity. This will just be x to the power 2n times dx. Now you can introduce in the sum and integral. Sum from n equals to 0 to infinity in the integral from 0 to 1 of ln x times x to the power 2n dx. Okay, good. Now I guess you know that if you have integral from 0 to 1 of ln x to the power n x to the power m dx, this will just be minus 1 to the power n gamma of n plus 1 by m plus 1 to the power n plus 1. I guess you know this formula of gamma function. If we use that over here, what we get is sum from n equals to 0 to infinity. Now this will just be minus 1 to the power 1 itself in gamma of 2 by, now this will just be 2n plus 1 square. Okay, now the sum can be written as sum from n equals to 0 to infinity minus 1 by 2n plus 1 whole square. Now you can clearly see that this sum is actually just the sum in the odd terms of the Riemann zeta function, just the sum of odd terms of the Riemann zeta function, and with a negative sign, of course. So for that, how we can evaluate this sum is negative times. Now for odd terms, we need to cancel just the even multiplications. That means 1 minus 1 by, now this is for Riemann zeta of 2, so 1 by 2 square. Yes, and then Riemann zeta of 2. So what I'm basically doing is I'm just multiplying by 2 square all the terms of Riemann zeta function, and then subtracting the original Riemann zeta with the newly formed even terms of Riemann zeta. So that's why I'm getting this. Now 1 minus 1 times, now this is 1 minus 1 by 4, so that comes out to be 3 by 4, and Riemann zeta is pi square by 6. Riemann zeta of 2 is pi square by 6, so 3 1s are 3, 3 2s are 6, and that gives me the answer as minus pi square by 8. Okay, now if you get minus pi square by 8, let me put that value over here. This expression is minus pi square by 8. I of 1 is equals to 2 times integral from 0 to root 2 minus 1 of ln x by 1 minus x square dx, and then minus times minus pi square by 8, that will just be plus pi square by 8. Yes, now I can multiply by 2, and that gives me I of 1 as pi square by 4 plus 2 times integral from 0 to root 2 minus 1 ln x by 1 minus x square dx. Okay, now we have made quite a good progress, but still there's a lot to do. Yeah, now our sole aim will be to deal with this integral over here. Yeah, we want to deal with this integral, and yeah, it will take some efforts to do it, but yeah, let us do now. Now this is kind of intermission of our series or of a movie that we're watching right now. Now the next part. Now for next part will be to solve this the remaining integral. Now let us say for some time that this number is just c, so that it will be easier to write. I didn't want to write these roots and negatives and all these things. So yeah, I of 1 is equals to pi square by 4 plus 2 times integral from 0 to c ln x by 1 minus x square dx. Yes, 1 minus x square dx. Okay, now what I'm gonna do is, now let us say that we want to break this into partial fractions. Let us try to break this into partial fractions so that it will be easy. Now this one is actually easy to break. The 1 by 1 minus x square will just be, okay, 2 times 1 by 1 minus x square is just 1 by 1 minus x plus 1 by 1 plus x. If you have this 2, this will be 1 plus x plus 1 minus x. X is cancelled out, so 2 by 1 minus x square. Yeah, so we get this. So we have I of 1 is equals to pi square by 4 plus integral from 0 to c ln x by 1 minus x dx plus integral from 0 to c ln x by 1 plus x dx. Yes, and now if we have this, now to solve this integral, now we need to notice that this integral is actually a polylogarithm integral. Yes, no, and before that what I'm gonna do is, I first have to reduce this limits of integral from 0 to 1, and then this is gonna be a standard polylogarithm integral, and that will be helpful for us. So reduce the limits of integral from 0 to 1. Obviously the thing that I need to do is to make a new substitution again, that w is equals to x by c. If I make the substitution, the limits of integral now gonna be from 0 to 1. Yeah, so I have I of 1 as pi square by 4 plus integral from 0 to 1, x is just cw, yes, by 1 minus cw, and dx is just c times dw. Similarly over here also, integral from 0 to 1 ln of cw by 1 plus cw, and dx is just c times dw. Okay, that looks good. Now let us try to separate the c's from w's. Yeah, because ln of w by 1 minus cw, that will be an standard integral, but not this right now. So that's why let us try to do it. I of 1 is equals to pi square by 4 plus integral from 0 to 1 ln of w by 1 minus cw times cdw. Similarly, plus integral from 0 to 1 ln of w by 1 plus cw times cdw, and minus the other things, integral from 0 to 1 c ln of c by 1 minus cw dw. Similarly, subtract the other one as well, integral from 0 to 1 c ln of c by 1 plus cw dw. Now if we subtract this, this are actually constants, and this is just 1 by the reciprocal integral, and this will just come in front of in terms of ln. Yeah, we all know that this comes in terms of ln. So we and also this two will be in terms of ln, but this also have negative minus in front of it. So let's do it. I of 1 will be, okay, wait, why I'm writing minus sign over here? This will actually be plus. Yeah, and they are not in division, they are in just addition, the multiplication, so this will be addition. Okay, so now this is just pi square by 4 and a plus integral from 0 to 1 ln w 1 minus cw times cdw. Similarly, integral from 0 to 1 ln w by 1 plus cw times cdw. Yes, and similarly over here this will just be plus c ln c, and then this will just be ln of, okay, both will have ln, but this will have negative sign, so that's why I'm gonna do it directly, and 1 by c. Yes, and now since there is c in both, 1 by c will be there. Now c cancels out, and we have ln c by this expression. Okay, and now this is from 0 to 1, this is also from 0 to 1. Yes, so we have I of 1 as pi square by 4, and then this is just ln of c, and then 8 1, this is 1 plus c 1 minus c, minus 8 0, this is just ln of 1, which is 0. So pi square by 4 plus ln c times ln of 1 plus c by 1 minus c. Okay, looks good. And now these two integrals, integral from 0 to 1 ln w by 1 minus cw times cdw plus integral from 0 to 1 ln w by 1 plus cw times cdw. Okay, now to solve this integral, again you have to notice another standard integral. Now another standard integral is like this. So let's say if you have integral from 0 to, sorry, let me write with the red pen now. If we have, let's say if you have an integral from 0 to 1 of ln of t by 1 minus a t dt. Again, we can write this as geometric sum, integral from 0 to 1 ln of t, and this is just sum from n equals to 0 to infinity of a t to the power n dt. Now let's understand the sum and integral. Sum from n equals to 0 to infinity, integral from 0 to 1, and then this is ln of t a to the power n t to the power n dt. Okay, so a to the power n is just a constant. Yes, a to the power n is just constant, but this is again the gamma function that I told you earlier. So this will be minus 1 to the power 1 gamma of 2 by n plus 1 square. Okay, good. Now again I can write this as polylogarithm function. How? Okay, minus, now if I take 1 by a over here, this will be sum from n equals to 0 to infinity of a to the power n plus 1 by n plus 1 square. Yes, so now this is this actually the definition of the dilogarithm function, 1 by a times li2 of a. Yes, so you see that this integral over here, ln t by 1 minus at is minus 1 by a li2 of a. Similarly, in place of a, if we replace this by minus a, we can get the next result as well, integral from 0 to 1 of ln t by 1 plus at, if we replace a by minus a. So over here what we get is 1 by a times li2 of minus a. Yes, Okay, so these two results are the necessary for the upcoming solution. So over here also we are going to use them. I of 1 is equals to pi square by 4 plus ln c ln of 1 plus c by 1 minus c. Yes, and now this one will just be okay, so we have the c already over here, we can take that out. Now this is just minus 1 by c li 2 of c. Yes, similarly plus, now I can take the c out, this one just be 1 by c li 2 of minus c. Yes, looks good, looks good. Okay, yes, it looks good. Now after this, what I can do is I can cancel the c's, I can cancel the c's. Yes, so we get I of 1 as pi square by 4. Yes, and then after pi square by 4, now this is li 2 of minus c. Yes, minus li 2 of c. Yeah, and then plus ln c ln of 1 plus c by 1 minus c. Good. Now since we know that c was actually root 2 minus 1, this also looks as a good answer, but we will try to find the answer in a closed form. Yeah, I guess it will also be right if we just leave it over here, but yeah, let's try to find the value. I of 1 is equals to pi square by 4 plus li 2 of 1 minus root 2 minus li 2 of root 2 minus 1 plus ln of c. Sorry, so okay, c is basically root 2 minus 1. So this is again over here, this ln of root 2, just root 2. Yes, by, now this is 1 minus root 2. Is it? Yeah, okay, wait, sorry, 2 minus root 2. This will be 2 minus root 2. Yeah, looks good. Yes, looks good to me. So this is 2 minus root 2 and then just root 2. Okay, good. Now after this we have I of 1 as pi square by 4 plus li 2 of 1 minus root 2 minus li 2 of root 2 minus 1 plus, now this is ln of root 2 minus 1, and this one root 2 cancels out, so we have root 2 minus 1 over here. And here if I want to take that numerator, I should introduce a minus sign over here. So I can make this minus, I can make that as minus, and then we will have 2 ln of root 2 minus 1s. Yes, this looks good up to now. Yeah, I probably think so. It looks good. Yeah, and now root 2 minus 1 is same as 1 by root 2 plus 1. Yes, and again that also gives minus sign, but since we have e squared, that will just cancel out, so I can also write it as root 2 plus 1 is squared. I hope you get that. Okay, good. Now if you get that, now we are just left with finding this expression. We are just left with finding this expression, and let us see how we find that. Now let me just reveal its value right now. The value of that expression, li 2 of 1 minus root 2. Okay, li 2 of 1 minus root 2 minus li 2 of root 2 minus 1. This expression actually nicely evaluates to its value is pi square by 4. Wait a second. Okay, so its value nicely evaluates to ln of root 2 plus 1 squared by 2 minus pi squared by 8. And now if we are able to find its value, then the integral will be solved. The integral will be completely solved if we find its value, and I'll also show you how we find that. So I of 1 is equals to pi square by 4. Yes, and now this is plus ln of root 2 plus 1 whole squared by 2 minus pi squared by 8 minus ln of root 2 plus 1 whole square. Okay, and yeah, after this we just need to do some arithmetic. I hope you all are good in that. Pi square by 8, and now this is this is not how come I get this is 2 not 8, sorry. My bad. Okay, by 2. So pi square by 8, and then this is just minus ln of root 2 plus 1 whole square by 2. This is finally our answer, but before we conclude this answer, I still have one more step to show you, because I haven't really told you how we get the value of li2 of 1 minus root 2 minus li2 of root 2 minus 1 is this absurd sum. So let me prove that now. Now to find its value, we will actually need some properties or identities involving polylogarithm function. Now let's just recall some identities that we know. Yeah, first of all, I guess you know about the duplication formula. Yes, the duplication formula. Let me just recall, though all of them will not be necessary, but let me just recall for the sake of recalling. So I guess you know the duplication formula of polylogarithm. Yes, which is something like this: li2 of x plus li2 of minus x. This will just be 1 by 2 of li2 of x square. Yes, this is the first one. Now second one is we have the reflection formula. The reflection formula, yes, it goes something like this. We just have li2 of x plus li2 of 1 minus x will just be pi square by 6 minus ln of x and then ln of 1 minus x. This is a reflection formula. Now next is Landens identity. Landens identity. I'm really sorry if this mouse pointer is somehow lagging. And the next is this can be done as li2 of 1 minus x plus li2 of 1 minus 1 by x will be minus ln x and its square by 2. The next is inversion formula. I'm just listing it out. We will not use all of them, but yeah, just for sake of recalling, that you will also have a good time recalling these formulas. Now the inversion formulas is li2 of minus x plus li2 of minus 1 by x. This will be equal to minus pi square by 6 minus ln x square over 2. This is our inversion formula. And the last one is the 3-die logarithm identity. It didn't really have a good name, so I gave it this name by myself, 3-die logarithm identity. Yes. Now this formula, sorry, I guess the spelling might be wrong. Okay, so the 3-die logarithm identity. Okay, this formula, this looks like this: li2 of minus x minus li2 of 1 minus x plus 1 by 2 li2 of 1 minus x square will be equal to minus pi square by 12 minus ln of x ln of 1 plus x. Yes, so this is the 3-die logarithm identity. Yes, now in this 3 formula we will be using these formulas to find the value of the required identity. Now, so over here, let me just give some ideas, and you can proceed yourself. Now in this formula number 3, if we substitute 2 minus root 2 over here, if we substitute 2 minus root 2 in place of x, and if we just substitute root 2 over here, and if you again substitute root 2 over here, yes, and after that if we add the first and the third, if we add the first and third and subtract the fourth, yes, we are going to get a good equations where these terms such as root 2's and minus 1 by root 2's will cancel out, and also there will be going to be an expression that is li2 of minus 1 is going to be there, and which you can find from its sum itself. Yeah, and from the sum itself you can find its value, which comes out to be minus pi square by 12. If you just substitute this value and like make the algebraic cancellations, we are going to get the value of li2 of 1 minus root 2 minus li2 of root 2 minus 1. Yes, just you need to do equation 3 plus equation 5 minus 4 and then make some manipulations. I'll substitute this value, and from there I have already done that, and we actually get the value that I told you, ln of root 2 plus 1 whole square by 2 minus pi square by 8. Yes, so let me know. I had already done that, but since it's going a lot of time, it's taking a lot of time, so that's why I have planned to skip it now. So just do this and you will get that our expression li2 of 1 minus root 2 minus li2 of root 2 minus 1, this will come out to be ln of root 2 plus 1 whole square by 2 minus pi square by 8. Yes, now yes, finally with this value I guess I can safely conclude this video. Yeah, we have finally solved this integral. Yes, this actually took 7 pages in my copy, and yeah, it looks pretty long, but yeah, these ideas were elementary ideas that anyone could have proceeded on. Not anyone, we do need some like ideas and the patience and the open-mindedness, just like how Sushi did it. Yeah, so yeah, I hope you guys now finally understood this solution. I hope you also enjoyed solving this problem and going through me. I hope this gave you some new insights, new ideas, how to go on solving the integrals, how to attack, and how to make these limits of integral nice, and then again observe the polylogarithms and various powerful techniques that can be useful. Yes, so hope you enjoyed the video. Look forward to seeing you in the upcoming videos too. Thanks for watching. Look forward to seeing you again soon.